Okay, morning. Okay, let's continue on the application of Laplace, solving differential equation. And we've got time, then we're going to look at a new concept. Okay? Yeah. So, when using Laplace to solve a differential equation, and basically the whole idea is you have a second order differential equation. Okay. And we take Laplace transform on both sides of this equation. Then we solve for y of s, right? And then we decompose this y of s to the simplest form that we can have. And then from the table that I give it to you to find the inverse, right, of the Laplace transform, which is the solution of this differential equation. Okay? So that's basically the procedure of solving differential equation using Laplace. Now, when it comes to decomposing this y of s, and there are basically three different kind of cases that we're talking about. Okay, the first one is you have a simple pose. The second one when you have a conjugate pose, and the third one is this one here when you have a repeated pose here. So this is basically the format that we were left in the previous lecture. So this is at y of s, the numerator has repeated pose here. So this s equal to s to the power 3, meaning s equal to 0 is repeated 3 times. And this s minus 1 to the power 2, this means s equal to 1 is repeated twice. Okay? Yeah. So when you have this kind of a case here, and the next step, when you decompose that, so this is how you're going to decompose it. All right? Yeah. So depends on the order of how many times repeated. So then you're going to have 1, 2, 3. Okay? In this case, order is 3, so 1, 2, 3 here. Right? Yeah. So, and the other one just for the s minus 1, and here is the same thing. So then the next step is to solve for ABC, or this ABCD at here. Okay. There is a formula associated with this kind of case. Okay, so I'll give you the formula, but I think in general, what I want you to do is just comparing coefficients. That should be enough. Okay, yeah. So let's say, for example, let's say solving this one here, just roughly comparing coefficients. So what do? We basically rewrite this decomposed one back into this numerator divided by denominator case. Okay, so then what you're going to have the numerator here is a by s squared s minus 1, and b by s minus 1, and c by s minus 1. And this is d s cubed equal to what? Equal to 2. Okay, so that's the comparing coefficients, huh? Then group the similar terms here. Okay, group the similar terms. So let's see how many s to the power 2, s cubed terms. There is one, a is s cubed, and d is s cubed. And how many s squared term? And a is 1, and that's negative. And there's a b here, and that's it. How many s term? There's a b here, negative. And there is a c. Okay, that's it. How many constants? We have only 1, right? Okay, we only 1. So basically now the other side is 0s cubed, 0s squared, 0s plus 2. So comparing coefficients, meaning a plus d equal to 0, negative a plus b equal to 0, and negative b plus c is 0, and negative c is 2. Okay, so that's comparing coefficients. Yes?
I thought you had to multiply all the denominators to the numerators.
Yeah. Well, see, this is s squared, s cubed, right? Yeah, s cube is a multiple of this s at here. I mean not a multiple. S cube is what do you call s is a common factors basically, right? Yeah. So when you put this thing back, this denominator here, this is actually basically s cube, s minus 1, and then on the top of that.
So multiply everything by that, s cubed, s minus 1.
No, see this numerator here is s here, right? Now, first of all, is it okay when I put this thing back into this one whole thing here? the denominator is s cubed multiplied by s minus 1, because the s cubed is basically the father of s and s squared, right? You don't need to multiply another s or s squared anymore, right? Is that okay?
Multiply that denominator by each.
Not multiplied by this denominator. So let's maybe just this guy here. That's a over s, b over s squared, c over s cubed. Okay. So when I put this one back into this fraction format, the denominator will be just s squared, s cubed. Then a at here, because this is s here, right? So a just basically just multiply as squared. See that? Because why? As squared over s cubed is a over s. And the b will just multiply by, what would that be taught? S. And c you don't change, so it's c. See, right? Yeah. Yeah, if you have another term s minus 1, so just s minus 1, s minus 1. Yeah?
You want the denominator to be the same as the other side. Okay.
Yes, basically you don't change anything, right? Yeah, and you don't add anything. Yeah. Okay, so I think this is very easy. So c is negative 2, and b is c is negative 2, so b is negative 2 again, and b is negative, a is also negative 2, and d will be 2. Okay, so plugging everything, okay, you got your fraction, decomposed fraction. Okay, so then what do I have here, right? So y of s, plugging everything there, so y of s equal to negative 2 over s, and b is negative, c is negative, and d is 2. So you can always double check, okay? So remember, when you have these numbers here, you can always plug in everything back into this fraction and combine them together. See if you can get back to your original y of s. Okay, so that's basically the way you verify if you got the right answer or not. All right? Yeah. This is actually important. Verifying whether you got it right or not, will determine what you're going to get in the end. Okay? Yeah. So I got this one here now, and then I'm going to use a Laplace table to find the inverse Laplace. So inverse Laplace, okay, is this y of t, and inverse Laplace basically look at inverse Laplace of each one of the term here. So some of them are a little bit new in here, but the first one, okay, that's okay. The first one is what? The first one, 1 over s term is basically unit step function. So the first one, that's 2, so negative 2 unit step function. Okay? Yeah. The second one is 2 over s squared. So okay, let's go see. I do have a 1 over s squared. Okay? And the inverse for that is t. So basically it means the second one here is what? Negative 2 t and then u of t. Okay? Yeah. The third one is 2 over s cubed. Okay, so that doesn't have any s to the power 3, but there's a general s function over here. So you see this is s to the power n minus 1 here. So which means if it's s cubed here, then the n will equal to 2. So which means that s cubed term here corresponding to a t to the power 2 term here, right? Yeah. So which means what? According to that formula, it's t to the power 2 changed to 2 factorial over s cubed, right? So t to the power of 2 is changed to 2 factorial over s cubed, okay? So this is 2 factorial 2 s cubed. Okay, so that's t squared is changed to this one here. So if I could look at this one here, does happen to be 2, that's good, right? Yeah, if this is not 2, just put it at 2 and then divide it by another 2, right? Yeah. So this is basically t squared u of t. And the last one there is 2 e to the power of t, u of t, okay? So you can take u of t out of this whole bracket and then multiply by everything. So that's your y of t, right? Yeah. Is that clear? Any questions? Yeah. So the skill I need you to master it here is how to properly decompose, okay, and how to find the inverse, okay, based on the given Laplace table. Now here's a general summary at here. Thing is not responding. Okay, so there on the page 11 of your textbook of the selector notes, computer is not responding. Okay. Anyway, so check page 11, okay, of that lecture notes. Okay, so there is a sort of a summary here as to when you have what kind of factor in the denominator as to what you're going to do to decompose that. Oh, there we go. Page 11, right here. So when you have a factor such like that, right, your partial fraction format will be looking like this. When the denominator contains a factor like this, well, make sure that for this particular one, make sure that this is actually the solution of this. When you set it to 0, the solution of that is complex conjugate roots. Then you separate it into this kind of format, right? Yeah. When you have repeated roots, then you separate it into this kind of format, right? If this is more complicated. When you have this kind of thing to the power of n, then you're going to do this, right? But I think we're really restricted to the first 3 cases, okay? Yeah. So for the repeated roots, chances are not going to be very high, the maximum 2 or 3, yeah, it's just too much, and then there can be a lot of partial fraction expansions. Okay. Was that clear? Yeah. Okay, so that's the 3 different cases, all right? Yeah, in terms of solving partial differential equation. The last kind of solving partial differential expansion, the last kind of application using Laplace to solve differential equation is such kind of case here. We're gonna use Laplace transform. Okay, use the Laplace transform on the dE on the differential equation with discontinuous input. Discontinuous input. So the input basically we're saying y double prime y prime by equal to f of t. And this f of t here, okay, or anything on this side here, okay, on this side, not just f, maybe just anything you plug it over here. So everything here that has something to do with the input. So the input here may not be a continuous function, may not be, let's say, sine omega t or cosine omega t. So it could be a piecewise function. For example, okay, I have a 2y double prime plus y prime plus 2y equal to a function, let's say, g of t. And giving initial condition like over here. And now my g of t is this. right? So this is the g of t here. You look at this g of t, and if you plot it out, what does it look like? So t exists only between t equal to 5 and t equal to 20. So this is a 5 and this is 20. Only exists between these two. And then when between these two, the value of the t is 1. So basically it's a box, right? It's a box. So this is what we call, it's a discontinuous. Basically it goes all the way here, and there's a jump, and it continues, and then there's jumping back here. So that's sort of a piecewise function at here. Okay? So it's not a very clean function like a e to the power something, sine something, or just a t, right? Yeah. Now when you have this kind of case right here, the way to look at this system is like this. You can look at the system as if you have 3 different inputs. One input is 0. The other input is 1. The other input is 0 again, right? So that's basically, you can look like this, but it just happens at a different time period, right? Yeah. So then there comes the way to solve this thing here now. Okay, so if I never teach you anything that I'm using Laplace to teach you how to solve this one here, so this is how you're gonna think about it, right? Okay, so between infinite to number t equal to 5, my input is 0, right? Yeah, so you're gonna solve basically a homogeneous differential equation up to where? Up to t equal to 5, right? So anyway, so you're gonna get y for t equal to something up to t equal to 5. Is that good, right? Okay. Now when t is greater than 5, your input becomes 1 now. So then you're going to solve your differential equation, which is 2y double prime plus y prime plus 2y equal to 1, right? Or u of t. But that's starting at the t equal to 5, huh? Yeah. Now the only trick here now is when t equal to 5, you're going to picking up right here. You're going to pick up what's left at the t equal to 5 from the first case, right? So you have your system. Basically, you get a 0 input, let the system go. So the system will behave until t equal to 5. So the system will give you something, maybe at the t equal to 5, y of 5 equal to something, and y prime of 5 equal to something, right? Based on the first solution. So this is going to be the initial condition for the second case. Okay? Yeah. So then you solve basically as usual, okay? And solve the different based on the initial condition contributed from the previous, okay, condition, yeah, up to where? Up to 20. So then you keep doing the next thing here. So that's how you do, okay? So that basically sounds a little bit complicated because you're going to have to go through 3 different steps, right? And in order to solve this one here. Now we have learned Laplace. Actually, we have a very neat and clean way to solve. Just use Laplace to solve this whole thing in one shot. That will be right. Right? Yeah. So let's see, how do we do that? Using Laplace meaning we're going to take Laplace transform of this differential equation. So this is what's going to happen here. So taking Laplace, okay, of both sides of this equation, and the other side, that's easy, it's a second order, so there's 2s squared capital Y of s minus s y prime s y of 0 minus, there's 2 here, minus 2 y of 0, okay, plus y of s minus y of 0 plus 2 capital Y of s, okay, equal to g of s, okay, equal to the Laplace of g of t, g of s. Okay, so I'll show you what the g of s is, okay, but that's basically what happens when you take a Laplace of both sides, right? Yeah. It happened that the initial conditions are 0 for this equation right here at a t equal to 0, so this is gone, this is gone, this is gone. Okay. So what we're left with is y of s bracket 2s squared plus 1, and hang on a second here, did I miss anything? Oh, I missed the s here, right? Yeah, that's right. Plus s plus 2, like this, equal to g of s. right? Okay, so this is the Laplace transform, then what happens here, okay? Yeah. Okay, so the next question is, what is the g of s? So g of s is the Laplace transform of this piecewise function. So this is g of t here. Now we learned unit step function. So this g of t basically is, what is it? U of t minus y minus u of t minus 20, right? So that's g of t, okay? So the g of s is the Laplace transform of this g of t. Okay, so g of s is the Laplace transform of this g of t. Okay, so the question is, what is the Laplace transform of u of t minus 5, right? Or what is the Laplace transform of u of t minus 2? So, but what is the Laplace transform of u of t? Which is? No. 1 over s, right? Okay. So the u of t minus 1 comparing to u of t is just a shift, right? It's just shift to the right by 5. So now that if you recall that we do have a formula, we have a property here. Here. This is the one here. So when you have a shifted function by amount of t, the corresponding Laplace transform is just multiply e to the power of negative s, then multiply by the amount of the shifting. Look at this property here. Okay, let me write it down here. So Laplace transform of g of t minus, let's see, what did I use? F here, right? F of t minus capital T, u of t minus capital T equal, okay, e negative s capital T capital F of s. Okay, yeah. Now you may think this is u of t, this is f of t minus u of t minus c. They're different, right? But what we're doing is we're trying to find u of t minus 5. So actually, u of t minus 5 multiplied by u of t minus 5, they are what? They're the same thing, right? This is basically u of t minus 5. Okay. So what's the inverse? What's the Laplace transform u of t minus 5? It's basically what? E to the power of negative. What's the capital T now? 5. So e to the power negative s, or 5s, then multiplied by f of s. F of s is a Laplace transform of this function f. The function f here is u of t. So Laplace transform u of t is 1 over s, and then multiply by 1 over s. Yeah.
I don't understand the part like how f of t minus t equals to u of t minus 5.
Okay, first tell me what's u of t. First of all, what does f of t? F of t multiplied by u of t is the same as saying f of t is just f of t. T is greater than 0, and 0 when t is less than 0, right? Yeah. So then, when you have a u of t minus 5, so that function itself basically exists. The function itself exists only when t is greater than 5. So then when I say f of t, okay, minus capital T, u of t minus capital T, this is the same way as saying this is f of t equal to f of t minus capital T when t is greater than capital T here, right? And 0 when t is less than t. So what's the difference between, if I change this one, if I change this guy to anything, can this one be u of t minus capital T? You can, right? So this is just a general function here. I can let this one equal to anything. So I can let it equal, I can let it equal delta, I can let it equal sine, right? But this time it's u of t minus capital T. Is that clear? Yeah. So this basically, that's why when you see what's the Laplace transform of this one here, that's basically, you match this format here, match the property, right? You can just use the property. Okay, take a second look at this property here, right? So sometimes you got to be a little bit flexible here, okay? So that's basically Laplace. Now then I can write it down here. The Laplace of this one here, negative 5s minus e negative 20s over s. Okay. So what we have here is there are two exponential ones over s here, okay. And then here's y of s equal to this. Now I can solve for y of s. Okay. So solve for y of s, which is e negative 5s minus e negative 20s over s squared plus 2s squared plus s plus 2. So that's y of s. Okay? Yeah. Okay, so this one looks pretty strange to us. We've never seen this inverse Laplace of this kind of thing, right? Yeah. Because in the previous case, when we're trying to find inverse Laplace, the numerator there is all just a clean fraction of function of s, not an exponential one, right? Yeah. So in this particular case, when you solve for the inverse, here's what happens here. You're going to actually trying to make use of this property again, basically. Okay. So you look at this one here. If I have a if I give you such kind of s function, look at this one here. This is s function here, right? This s function. If I compare the s function to the first one here, isn't that this one the similar like this one here, right? Yeah. So which means maybe what I can do is I can just look at this 1 over s bracket this guy here. Find the inverse of that. So this e to the power of st, all it does is it just means there's a shifting in the time domain. I heard that. Yeah. So right? So this is basically what's going to happen here. Okay, so let's do this. So this y of s, I'm going to say this y of s equal to m of s multiplied by e to the power of negative f5s e to the power of negative 20s. Okay, so I'm going to do this. I'll show you what happens here. This m of s is basically the 1 over s 2s squared plus s plus 2. Okay, so this is m of s, right? I didn't change anything. I just rewrite it into the format I wanted to use. Okay, yeah. Is that clear? Yeah. Okay. Can we find the inverse Laplace of m of s? That's easy, right? How many I have s over here? There's 2s plus s plus 2. So it depends on the type of roots this one have, right? So you can see, you'll see that the roots this one have is a complex conjugate root. So I'm not gonna decompose this anymore. So the partial fraction expansion for this one is gonna be OE over s plus bs plus c over 2s squared plus s plus 2. Okay, so you're gonna be able to solve ABC. Yeah.
So where did you get the expression plus?
Yeah, just a second here. I'm coming to that. Okay, so this is m of s. This you can easily find the inverse Laplace of m of s. Okay, but what we want is inverse Laplace of y of s. Okay, so now if I look at this one here, I have m of s multiplied this, m of s multiplied this. Okay, so then I'll just show you what it is. Suppose we're going to end up with m of t. Okay, suppose we're going to have m of t here. Now, y of a t is inverse Laplace of capital Y of s. Okay. So looking at this is y of s, which means it's going to be inverse Laplace of this minus inverse Laplace this. Is that good? Okay. So there's not much of excitement here, I guess, end of the term, and so I'll just go in. Right? So this inverse Laplace will be just simply the inverse Laplace this term and the multiply inverse Laplace this term. Okay. Now this is time I'm going to make use of my property again. So what property did we just use? you look at this. This is the property that we used at the beginning here, right? This is the property we used at the beginning. So the property is this. So Laplace transform of f of t, not f of t, t minus capital T, and u of t minus capital T equal e to the power of s, st and capital F of s. Okay. So let's do a little comparison in here. This m of s is this f of s. This e to the power of 5s is this guy here. Then the inverse Laplace of such s function, according to the property, will be just simply, will be what? F of t minus capital T, u of t minus capital T. So which means, okay, this inverse Laplace over here, continue here, for the first one here, for the first one, what will be the inverse Laplace? M of t, and then minus 5, multiplied by u of t minus 5. Is that right? The second one here will be m of t minus 20, u of t minus 20. See that? Yeah. See, this is the purpose of doing this step here. And where is m of t? Where is m of t from? This is basically shifted m of t. This is basically shifted m of t. Where is m of t from? M of t is from here. Okay, it's from here. Okay. So this is y of t here. Okay, that's the overall picture. Was that tricky? Yeah. But you see, this is very clean here. You know, in one shot, you get the solution for y of t, right? Get solution for y of t. Instead of you know, you solve it in 3 different steps. Okay, it depends on 3 different, like you have 3 different inputs. So the property that we used here is this so-called time shifting property. This is a time shifting property. Now, I think you actually used this property in the first assignments there. Okay, this time shifting property is quite useful there, right? Time shifting, particularly when you shift to the right, it's essentially called a delay. Okay, it's essentially called delay. And delay is a very common phenomenon in a practical system. So then, how do I know whether my system have a delay or not? Usually, so when you look at the transfer, you look at this s function. If there is a e to the power of negative something s, so that basically means there's a delay in the system output. Right? You look at this y of s, this is output here, right? And y of s contains a e to the power negative something s. So that means there is a delay in the output. Yes?
Do we not have to solve for m of t?
Yes, you do. Yeah, I just didn't solve for the m of t here. Yeah. So, but the solving for the m of t is pretty much the same procedure as we have gone through for the 3 different cases, right? So I'm not going to solve it here anymore. So you can look at the lecture notes or try to solve this one by yourself, comparing coefficients, right? There's nothing new at it here. Okay. Yeah. Was that clear? So one assignment is a practice of this. And in my lecture notes, I have given you some hints on the particular assignments. So take a look at this this procedure here, right? Yeah, it's quite useful. Yeah. Okay, so here's a drawing of this one here. This is the system that we just did, okay. And here's a drawing in here. So as you can see, because initial condition are 0, so when t is less than 5, the system basically, there's no initial condition, the system just basically not moving, right? So it's all 0. And at the t equal to 5, there is a jump of the input from 0 to 1. So then the system started to behave based on this new input. So the system behaves, there's oscillation. Basically, if there's oscillation, actually, remember, what do we call this kind of system? Mechanical, for forced vibration, there's 3 different kind of a name for that, right? One is overdamped, critical damped, and underdamped. So when you see this one here, it must be a underdamped system. So it oscillate up to 20, right? Up to 20, you see, it hasn't been settled down yet. Okay, so there's no chance for it to settle because the time duration from 5 to is not long enough. If it's long enough, you'll see the vibration basically settles down, right? But at the time to 20, there's a change of the input. The input changed back from 1 to 0. So it doesn't settle down really, but it started to basically be responding to the t equal to input to 0 now. So input back from 1 to 0, so the system starts to oscillate around this 0 point here. So now there's no change in input, so you have enough time for the system to settle down in here. Okay, yeah, like this. So that's basically the behavior system. If you look at this the solution here, suppose you got something here, something and here. So that's actually give you an idea of a piecewise function too, right? Yeah. Okay. Okay, so that's basically all about application of Laplace transform, right? And this is a very useful tool. Laplace transform does not restrict to just solving differential equation. There are many other things here. Okay, so here's another thing for Laplace transform, particularly for those people going to mechanical and electrical. You are going to learn control system in the further the third year. And there you will use Laplace a lot, actually. Not a lot, quite a lot. Yeah, quite a lot. In terms of studying system response and control a system. But one of the things I want to point out here is, in terms of Laplace, is called transfer function. So this is a new concept. This is just a new concept, but behind this new concept, that's nothing new, okay? So you'll see that. So transfer function and impulse response. And there is a connection between it. Now we're back to the impulse function now, impulse response. Okay, so now tell me, what is the definition of impulse response again? Yes. Yeah, so I think I emphasized so much in the midterm. I give you 5 points of question there. There's still a lot of people who couldn't answer the definition of impulse response. Okay. Now, maybe I'll just give you another 2 points of in the final. What is the definition of impulse response? Yeah. Okay. So there is a connection between these two here. Okay. Yeah. But first of all, let's take a look at what is the transfer function. Okay. Definition first. So here's what we do. So I'm going to use a system right here, and I give input to the system. We got an output from the system. Okay. And this is supposed to be the LTI system, right? When you have this LTI system here, then what we're going to do is, let's take Laplace of both sides of this input and output. Is that good, right? So if I take Laplace both sides, here is capital X of S, right? Capital X of S. And here is Y of S. Okay, here's Y of S. So the system, okay, when you take Laplace transform here of the input and output, the system itself, okay, we can also use a S function here to represent the system. So we're going to use this so-called H of S to represent the system here. All right? Yeah. Then what's this H of S? This H of S is defined as the ratio between output and input. So this is H of S was defined there. Okay. This definition H of S basically is what we call transfer function. Okay, so this is basically called transfer function. Okay, yeah. So in the lay words, transfer function is basically the ratio between the Laplace transform of the output over the Laplace transform of the input. Okay, that's basically very simple, right? Transfer function. That's basic. If you have the if you have Laplace transform x y of s or x of s, just divided by each other. That's transfer function.
So in the second system, h of s is just multiplied with x of s. Get y of s?
Yes. Basically, this guy here. Well, I'll explain what happens here. Essentially, the way that the transfer function is defined here is important. Basically, the original system can be represented using this s function h of s. Okay, so it is h of s, as you're going to see, contains the dynamics, the characteristics of this system. Okay, you give input to the system, or you give the input to h of s, then as you can see from here, then what's my output? My output will be basically the input multiplied by the transfer function. Okay, yeah. So that's the importance of the transfer function here, right? So we'll see it. The next one here, I'll show you how do we obtain the transfer function. Very simple. Okay, yeah. So let's say I have a system in here. Okay, a differential equation. We always use differential equation to represent a system. Okay, so here's my differential equation. I have a differential equation which is 9, okay, y double prime plus 12y prime plus 13y, okay, over equal to 2, okay, dx over dt plus 3x of t. Okay, so I change the notation just slightly. When I look at this one here, what happens is x of t is input, and the y of t is output. Okay, so the differential equation, the variable is always y, that's always output. Okay, so here is a system, and if I consider this diagram, x of t is input, y of t is output, right? Now, what will be the transfer function? How do we do that? According to definition, transfer function is the ratio between y of s and x of s. So then what do? We're going to take Laplace transform, okay? We're going to take a Laplace transform both sides of this equation here. Okay? Both sides of this equation. Yeah. Before we do that, I think I missed one important thing here, okay? When we try to obtain the Laplace transform, when we try to obtain the transfer function here, okay, I'm going to use the red letter, we're going to assume zero initial conditions. Okay, assume in zero initial conditions. Okay, so we'll see why this is important. Okay, so remember, when you try to obtain, when the question asks you to obtain transfer function, the premises is zero initial condition. Okay, yeah. So then over here we're saying what is the transfer function for this system. Okay. If I say what is the transfer function for the system now, then don't ask me what is the initial condition. So what's the initial condition? 0. Yeah. Yeah. Trust me. Every time in the final exam, there's student ask, what's the initial condition of this one? Because transfer function. I say I don't know. Yeah. If you don't know, then how do I find a transfer function? You should know, right? So why? Because transfer function meaning 0 initial condition. All right. Yeah. So getting back here, I'm taking Laplace. Okay, taking Laplace, and then this originally this is 9s squared y of s minus s y of s minus y prime, right? Because 0 initial condition, so those are all gone. So when you take a Laplace take a Laplace transform, this is just 9s capital S squared capital Y of s plus 12s y of s plus 13 y of s. Okay, is that good? Yeah. The other side is 2s capital X of s plus 3 capital X of s. Okay. So what are we trying to find? We're trying to find a ratio, right, between the Laplace transform of the input and the Laplace transform output. So let's obtain the y of s. This side group the similar terms. The other side group the similar terms. There, right? Group the similar terms. Okay. So transfer function is h of s equal y of s over x of s. Okay, over x of s. So here is what we obtained based on the system after taking Laplace transform. So now you look at this one here. Can you get the ratio between y of s and x of s now? Now this is important. There are many students make a mistake from here to here. So I want you to write it down here first. Okay? Yeah. Many of you make a mistake. So what will be the ratio? Write it down there, and then I'll write down mine. Is that what you had? Yeah? How many different? That's okay. If it's, well, there should be some. So anyway, my point here is, what I'm saying the mistake is, a lot of you reversed order here. Okay? Put this on the top, this on the bottom here. And that's very convenient mistake. But that mistake will cost you quite a bit, because we're going to need a lot of more steps from here to the rest. Okay? Yeah. So always remember, how do you get? You need to get back to this one here. So this one multiply this equal to this multiply. So that's how you get back. Okay? Yeah. Double check all the time. So this is a transfer function. That's it. All right. That's pretty easy. Okay. So I'll explain what exactly this transfer function will do to us. Okay. And how is that connected to the impulse response in the next lecture.